In this last tutorial video, I will show you what happens when you bias evolution of a network. So we'll consider biased evolution of somatogenesis. And so this is going to be a simulation very similar to the one I defined in the other tutorial video on project creator. So it's the name is different. It's called SOMAI-test. And the slight difference too is that I made repression slightly stronger to really help evolution. And so let's look at the evolution of fitness for the first seed. And so you see it works very, very well. It just decreases. It must be a good simulation. So let's check that the initial network topology is the one that we have chosen indeed. And so this is the case. When I plot the generation 0 layout, we have mutual repression, activation, and then self-repression. So that works. So something quite interesting is happening around generation 310 for the network topology. So let's look exactly at generation 310. And so if I look at the network, so you see the difference. So there is an extra gene, and then there are many other negative interactions. And so why is it interesting? It's because you have many potential oscillators in a network like this. You have this negative feedback loop here. You also have this kind of longer negative feedback loop. So you have potentially 3 time scale interacting, 3 oscillators interacting. So what is happening and what is actually generating the pattern? So as a start, let's check that there is indeed a good pattern. So we run the dynamics. Okay, and so if we run the dynamics, well, we clearly see we have a nice pattern. The other big difference with regular simulation of somatogenesis is that here in this case, you clearly have an alternation of different genes. So output 0 and species 3, and so that creates different domains. And so now if you get the actual oscillation, plot the dynamics, well, it's kind of oscillates and then it stabilizes. So that looks like a regular clock on reform model. Okay? So now let's see what happens when you can change the topology to somehow test what are the main mechanisms. And so again, there are at least 3 negative feedback loops in the system. So what is interesting to do here is to remove the short ones, so which would expect to be some kind of short time scale oscillation, delayed oscillation. So let's remove the negative feedback loop on S2 and S3. And so this is done with this little new cell here where you can choose the interaction you want to remove. So let's remove first the interaction of S2 on itself. And so you have to replot the network to see what happens. And then you see remove S2. And then let's do the same for S3. Okay. Okay, so we have removed the negative junction. So now we only have one long negative feedback loop in the system. Okay, and so now let's see what happens on the dynamics. So initially on the profile, you add this kind of, small size pattern, small stripe. And now if you run the dynamics, okay, we plot the profile. And then it's very interesting because now we have this kind of long pattern. And so if you look again at the dynamics in the last cell here, then what you have this kind of much longer period oscillations happening. And so this is why you have this big pattern. And so of course here, this comes most likely from the fact that you essentially add some short feedback loop that are oscillating essentially rapidly. And then when you remove them, you somehow reveal a longer oscillation and it's still making pattern. Obviously, it makes less pattern, but it's still a clock on reform model. And so it's quite interesting to see that might have hidden networks like this that could be semi-functional in such evolutionary simulation. What you can do next is that if you can really want to break the system, you can start removing nodes. So for instance, let's remove node S3. And so we expect that things are not going to go very well if we do that. So let's do this. So you can remove any node except inputs and outputs. So let's look at the network. And so now we have this network. So let's look at the behavior of this network. Okay. If you look at the profile, it's basically only one stripe. This is actually the stripe module that was observed in the first evolution simulation. We only have one stripe, and so now we broke the oscillation, and of course we can look at the dynamics in the very last cell. We basically have, it just comes up and down. So this is an illustration about how to bias evolution to get some less trivial result maybe, and also to remove nodes in a network. And so thank you for your attention, and I hope it was useful.